Good afternoon. Welcome to the Heidelberg Joint Astronomical Colloquium of today. It is a great pleasure to welcome Lisa Kewley from the Australian National University in Canberra to give a talk about galaxy evolution in 3 dimensions. Before we start with the colloquium, let me say a few words about the speaker. She's a very distinguished scientist in observational astronomy working on galaxy formation, galaxy evolution, looking at many different observational but also theoretical aspects of the problem. She started out studying in Adelaide in Australia, did her PhD in Canberra at the Australian National University. After that went to Cambridge, to Boston, as a CFA fellow. After that, she got the prestigious Hubble Fellowship, which she took to a very beautiful island, Hawaii. She, after that, got a faculty position at the Institute for Astronomy in Hawaii. And in 2011, she moved back to Australia to take a faculty position and a full professorship at Mount Stromlo Observatory in the research school of, physics and astronomy?
Astronomy and astrophysics.
Astronomy and astrophysics at the Australian National University. She has received throughout her career many prestigious prizes. Let me name a few. The Annie Jump Cannon Award for Women in Astronomy for specific achievements in science. There is the Newton Lacey Pierce Prize in Astronomy. In 2014, she was elected a Fellow of the Australian Academy of Science. She also got the prestigious Future Fellowship of the Australian Research Council, and 2 years ago, I think it was, 3 years ago, she got the Laureate Fellowship of the Australian Research Council. So, she's also the head of the Castro 3D Excellence Cluster in Australia, and we are now looking forward to your talk. Welcome.
Thank you. So I'm just going to check, is my microphone working? You can hear me at the back? Excellent. Okay, so today I'm going to be talking about galaxy evolution in 3D, and this is a real work in progress. We've been working towards this for several years now. We're just at the stage where we're getting science out from these large integral field surveys. So I'm going to be showing you how we get the science out of these surveys in different areas of galaxy evolution, and then what are the exciting science results that we have at the moment, and then at the end I'll talk about our future. Now, credit goes to a fantastic team of postdocs and students, so I'm going to be showing you their work today, and I'd like to highlight 3 of my former students who are now here in Heidelberg, and Yiting Ho is in the audience. The other 2 are at a meeting in Cambridge today. Now, just a quick summary. I'm going to give an introduction for those of you who don't do spectroscopy. I'll give a bit of an introduction into how we derive properties of galaxies in order to understand galaxy evolution. And I'm going to be talking about some of the major physical processes that we're trying to probe, and that includes gas inflows, gas outflows, connection between star formation and AGN, and then how star formation, AGN, and shocks affect the overall host galaxy. And finally, I'll give some conclusions, and then I'm going to talk about the future directions of this field, particularly in Australia. Okay, so this is a spectrum of a nearby starburst galaxy, and these are standard emission lines in the optical spectrum that we use to derive properties of galaxies. And one spectrum, you can get a lot of properties of galaxies. For example, you can derive the metallicity, and we use the oxygen lines and H beta as well as the H alpha and N2 lines to derive metallicity in nearby galaxies. And I'm going to define metals. We use log O and H plus 12, and the reason we do that is because it's easy to measure, and you can see very strong oxygen lines, but it's also the dominant element by mass in the universe, and it's also a tracer of the electron temperature of the gas. And so oxygen, in fact, because it's sensitive to the electron temperature, it actually traces the overall amount of metals in a nebula, because as you add metals, they actually cool the nebula. So metals act as coolants. If you add more metals, you cool the nebula, and then you get less collisional excitations of the oxygen line. So these are sensitive to the overall metallicity. What do I mean by metals? Well, you're all familiar with the periodic table. Extragalactic astronomers have a different periodic table. This is different to theorists and stellar astronomers, for example. So we have hydrogen, we have helium, metals. Okay, everything else is metals. Now, we also can measure the star formation rate using the oxygen 2H alpha line, the electron density using these density-sensitive doublets, sulfur 2 and oxygen 2, and we can derive the ionizing source. So this is whether you have star formation or AGN, using the ratio of these lines, particularly oxygen 3 divided by H beta, S2 and H alpha, O1 and H alpha, and N2 and H alpha. If you have shocks in a galaxy, and that may be driven by galactic-scale winds, or you may have shocks from an Aegean driven outflow, jets can produce shocks, and galaxy collisions also produce shocks. And so you can measure those using a range of emission lines. You measure the ionization parameter, which is the ratio of the oxygen 2 to oxygen 3 lines, and this tells you about how well a radiation field is able to ionize a gas. It's defined as the number of hydrogen ionizing photons per unit area per second divided by the hydrogen density, as in centimeters per second units. And then if you want to derive those shock properties, you can use these line ratios again, and it's actually the sulfur 2 and the O1 divided by H alpha are actually the best diagnostics of shocks, because shocks produce a very hard radiation field. And if you have a hard radiation field, at the very edge of a nebula, you have a long partially ionized zone where you still have ionizing photons able to ionize the gas, and sulfur 2 and O1 are produced in this extended partially ionized zone. And so this zone becomes very long when you have shocks. And so these lines are very strong in shocked regions in particular. Okay, so we want to understand spiral galaxy evolution. So we want to understand how galaxies came from the very early universe into the galaxies that we have around us. And in particular, we're trying to understand how they undergo transformative processes as they evolve. And so I'm going to talk about galaxy evolution. And since the World Cup's on, I thought instead of just giving you a galaxy model, I will do the World Cup model. Now, I was going to show the World Cup model for the most recent match that Germany was involved in, but I thought that would be too depressing. Galaxy evolution is not depressing, so I decided we'd just take a little bit of a path back in time, and we'd just do last year's final. Was it the final? No, maybe it wasn't the final. Let's see. Inflows. Okay, so this is our galaxy, big stadium. We have inflows into the stadium. You've got to have the inflows, and then the inflows, well, actually there's a couple of inflows. Oh, there's another one. And they drive star formation. So your gas drives star formation, and the star formation can produce metals up here, and more star formation. And star formation, if you have enough star formation in the center, can drive some outflows. I got pretty fancy with these animations. And also, the inflows may also fuel an AGN. Now, your AGN can also quench star formation, as is happening right here in real time. And then the AGN can also drive outflows. Those outflows could be driven into the outskirts of the galaxy, which would then come back in, or they could be driven out of the galaxy entirely over here and go into the intergalactic medium. And so this picture, a different image of it, but the same thing is here. And the problem is that there's a lot of questions that we haven't been able to answer about this picture of galaxy evolution. Very many questions. So, for example, when did the gas inflow occur? How much? By what mechanism is it fueling star formation and AGN? Where is the gas falling into the galaxy? How do stars produce the metals, and then how do these build up in disks like our Milky Way? How common are outflows? How much mass is lost in the outflows? And how much metals are entrained in the outflows? And is there a connection between star formation and AGN? and how much of the outflows goes back into the galaxy and how much remains out in the intergalactic medium. So there's a huge amount of questions that we haven't been able to answer yet in galaxy evolution, and integral field spectroscopy is what we're using to answer many of these questions. So these are the questions we're aiming to answer at the same time with integral field spectroscopy. So we're studying inflows and fueling of Aegean and star formation. We're studying outflows and also how do metals build up in disks. And we can do all of that with integral field spectroscopy because not only do we have the information, spectral information per pixel, we call it spatial pixel, so a spaxel across the galaxy, but also we have velocity information as well, and that's really critical to be able to do this work. Okay, so the surveys that we're using are some Australian and some international surveys. In particular, we have the SAMI survey, which has now achieved 3,000 galaxies, so 3,000 nearby galaxies with data cubes. These are in the field as well as in clusters. We also, to supplement this sample, we also have an Aegean sample that we've been taking at the Australian 2.3 metre integral field spectrograph, and we have 140 Aegean in that sample. And then we're supplementing these samples with other surveys, Callifa, which is high mass galaxies, and then Manga eventually aims to have 10,000 galaxies. And so the SAMI survey, I'm going to focus a little bit on that because we have so many galaxies now, we've been able to do some very good science with it. So the SAMI survey is undertaken on the Anglo-Australian telescope, and it uses hexabundles, so these are hexagonal shaped fibre bundles which are fused together, and that minimises light loss. And in the next generation SAMI, which is currently being built at the moment and is due to go on the telescope early next year, is called Hector. And that instrument, instead of having humans place the fibre bundles on plates for every single plate, we're using piezoelectronic robotic positioners. These are pretty cool things. It's a bit like using your mobile phone, you put it on the floor and you're trying to vibrate it across the floor to get it to a specific position. That's what these piezoelectronic robotic positioners do, and they're very, very accurate. And so we're building these for several telescopes at the moment, including the Hector instrument. Okay, we're also using the ANU WISE telescope, which is not based on fibres. This is a regular beam splitter spectrograph. The advantage of both of these spectrographs is the very high spectral resolution that we're using. And because we need to have about 30 kilometres per second in the red as well as in the blue. And the reason for that is because when you're looking at a galaxy with very complicated kinematics, you can have wind here, you may have an Aegean in the centre, you may have star formation around. You need to separate out all of those components. And the only way you can separate those components is by separating them in velocity space. So you can have individual components contributing to every single emission line. We need to resolve them out. And that's why we have high spectral resolution. And so these two Australian surveys have the high spectral resolution of the large IFU surveys. Okay, so I'm going to show you how we are looking at inflows using integral field spectroscopy. And here is an example. This is from Yiting Ho's work from part of his previous PhD thesis. And this is H alpha, oxygen 2, and here is a map of a metallicity sensitive line ratio. And so you can see that within these integral field data, we can derive metallicity maps or metallicity gradients, but we also have velocity information, and we use all of this information to understand galaxy evolution. Yiting derived metallicities using this method for a large number of galaxies, and what he found was that the metallicities, if you normalize by galaxy mass, or galaxy size, so this is the 25th isophotal radius that the galaxy metallicity gradient is normalized by. So this is a metallicity gradient, and 0 is a flat gradient, -1 is a steep gradient. And you can see that all of these galaxies across this large range, it's almost 4 orders of magnitude in stellar mass, all of these galaxies have roughly the same gradient, within a large scatter. And so this means that the galaxies must have had similar histories, so similar star formation histories, but also similar feedback or outflow histories as well. Otherwise, you couldn't get all these galaxies across this whole mass range having very similar metallicity gradients once they're normalized by size. So this is really important. This gives us a benchmark gradient, so we know that isolated spiral galaxies all roughly have the same metallicity gradient. And so what that means is that if a galaxy's had a recent dynamical disturbance, we'd see that in the gradient. We know what it should be if there's normal spirals, and so we can look for differences. That's what we did. And so we started looking at metallicity gradients in galaxy mergers because merger models predicted that gas would fall in from the outskirts of the galaxy, fall into the center. And if that's occurring, you would be bringing in pristine gas, and you'd be diluting the metallicity in the central regions of those galaxies, and perhaps you'd be flattening metallicity gradients. So we started to look for this. In addition, so here's an example of a simulation. So we worked with Paul Torrey at Harvard and Lars Hernquist to produce some simulations and predictions of the metallicity. And so throughout the merger, you've got gas falling in. It streams in down the spiral arms because of the tidal disruptions from the merger, and then the spiral arms are also, you can see they're also distorted and pulled away. So this is also going to be affecting the metallicity gradient. And then you can see there's just, the gas is just thrown around everywhere. So if you're looking at the gas phase metallicities, which is what we're looking, you would be seeing the effects of the merger, the recent effects of the merger on those gradients. And so with Paul Torrey, came up with these predictions of how the metallicity, so this is the central metallicity in a merging galaxy, would change as a function of merger progress. So here, the two galaxies are having their first close passage, and this triggers gas inflows down the spiral arms, and so you get a dilution of the central metallicity. Of course, this then triggers star formation in the center, and that star formation enriches the gas, and so you would expect to see an increase perhaps in the metallicity for a time, but then final coalescence leads to a huge dip in the central metallicity, so you're bringing in more gas a second time, and that dilutes the metallicity. And then what happens after that depends critically on whether you've got outflows. And so you can either, this star formation that's been triggered here would enrich the gas, but you may be driving the gas out or quenching star formation. If that happens, you're never going to recover the gradient up to what it was in the spiral galaxies before they merged. And so tracing metallicities in late stage mergers is critical to understanding the impact of outflows on star formation and on build-up of the overall metallicity in the disk of the galaxies. This is very complicated because we often have AGN and shocks and star formation in those late stages of the mergers, and so we need to separate all three of those. Okay, so first we started looking at metallicity gradients in merging galaxies. Do the gradients are they driven down by gas inflows? And so what we found, we looked, this is before, we started this work before large, wide IFUs, and these galaxies are very far separated, so we used ELRIS as a multi-object spectrograph on Keck, and these are the results. And so the normal spiral galaxies, there's a few shown here in solid lines. We've got M83, the Milky Way, and M101, and all the rest of the lines, the dashed lines and dashed lines here are from our pairs, our galaxy pairs. And you can see that all of the pairs have flatter gradients than the isolated spiral galaxies, every single one of them. So this is a smoking gun for gas inflows. But these are only pairs. What happens at the late merger stages? You saw that maybe the metallicity would be built up and then maybe the metallicity drops again. Does that happen? So we looked at late merger stages. We compared with the benchmarks, the eating that I showed you before, and here we have the metallicity gradient as a function of merger stage. So this is the metallicity gradient. 0 is a flat gradient, and here you can see that you start off with steep gradients for isolated spiral galaxies. That's normal, consistent with the Eating's benchmark. As you get wide pairs, the gradient flattens. Close pairs becomes flatter, and late mergers becomes even flatter still. Now these are only the galaxies where they don't contain an AGN or shocks, because at this point in 2012 we were unable to separate star formation from shocks and from AGN when they're contributing to the same spaxel. I'm going to show later in the talk how we're now able to do that, and we've just been able to do that recently. But still, this shows you that we are driving inflows all the way through the merger, even at the late stages, as predicted by the simulations. Okay, the other thing that you can look for, and this is results by Sam Richards, and this is from the SAMI survey, and Eating has a very beautiful example of one of these as well. You can look for low metallicity objects inside galaxies. This is a dwarf galaxy, and this is really interesting because it's got a region here with very strong H alpha, but that particular region also has very low metallicity. So this is a BPT diagram, we call it, which is based on the O3 and H beta line ratio and the N2 and H alpha line ratio, and there's a metallicity sequence across here. So up here is low metallicity, down here is high metallicity. And so this region is very low metallicity, and so the conclusion is that we must have brought in a large amount of pristine gas just here. So perhaps there's been a small, a really tiny thing, like a miniature dwarf galaxy has fallen in recently to this galaxy and has produced a fairly large region on this galaxy of pristine gas. Relatively pristine gas. Now, one question we get asked and that we've been looking into recently is what are we missing at the spatial scales of these large surveys? So large integral field surveys typically have spatial resolution of 1 kiloparsec per pixel. Within 1 kiloparsec you can have a lot happening. So you're not resolving by any means your H2 regions, and so what is the effect on things like the metallicity gradient? And so we started using the Typhoon survey, which is led by Barry Mador. And what Barry's been doing for about a decade or more, he's been going down to Palomar and putting a long slit on galaxies and then stepping that long slit across the galaxies and building up data cubes that way. It's a really time-consuming process, but what it means is that you can get data cubes of galaxies that are much larger than we could do before MUSE, for example. And we have the oxygen 2 lines, which are important for measuring metallicities. And so here's the native resolution of this particular galaxy in Typhoon, and it's 41 parsecs per pixel. We can resolve the H2 regions. If you degrade the resolution, this is what you would get with the SAMI survey or the MANGA survey. And so you can see it's pretty different. And so the question is, if you are not resolving your H2 regions, how well can you measure the metallicity gradient actually? And it's really disturbing. So this is the metallicity gradient. Here's what happens if you take that galaxy and you degrade the resolution and then try to measure the metallicity. Here's the native metallicity. These are 2 different diagnostics. And as you degrade the resolution, the gradient becomes flatter, like that. Now at high redshift, a lot of flat gradients have been measured. They have spatial resolutions of about this, even with adaptive optics and gravitational lensing. And so the question is, are they really flat or not? I'm not sure. Probably not. And so this is by my current student Henry, and this paper's just been submitted. And you can see he went further and started looking at the diffuse ionized gas. So around all these H2 regions is gas that's been ionized by the light that's escaped the nearby H2 regions. And so the light that escapes the nearby H2 regions is absorbed by the H2 region. And because it's absorbed by the H2 region, it's actually got a fairly hard radiation field because the softer photon's been absorbed. What that means is it produces very strong emission in lines like sulfur 2, N2, lines that are sensitive to a hard radiation field. And what we can do is we can now separate out the diffuse ionized gas, called the DIG, and the H2 region metallicity gradient. So this galaxy has a steep metallicity gradient of minus 0.1. And the DIG, if you just thought, okay, I'm going to throw my DIG through my normal metallicity diagnostics that I do, and you would get a flat, it'd be almost 0 gradient. Okay, if you were blind, you didn't know where the H2 regions were, and you have 1 kiloparsec resolution, you'd get this, which is, of course, a combination of the DIG and of the true gradient from the H2 regions. If you try to recover the gradient, you can't, because with 1 kiloparsec resolution, you don't know what the DIG is, and you don't know what the original gradient was. And you still can't recover the gradient. This is the recovered gradient until you have native resolution. Okay, so this is pretty depressing actually for measuring metallicity gradients at high redshift and even with the SAMI and MANGA surveys. What we're doing now, and we've been talking with Ralph about this, is to model the dig. If we can model the dig, and we're also measuring it now for more galaxies in the Typhoon survey, to understand whether it's fairly consistent across galaxies, how it changes for different galaxy types, because it's going to depend on the stellar populations and their ages, because it depends critically on the ionizing radiation field that are produced by the stars and then absorbed by the H2 regions. So this is work that's ongoing, but really, really important implications for measuring gradients. Okay, so I'm going to show you how we measure outflows in galaxies, and this is less depressing. This is very exciting. So this is some work that was done by my former student, Jeff Rich, and he looked at integral field data of galaxies which are late-stage mergers, and that's because we wanted to measure metallicity gradients in them. But we found that most late-stage mergers are filled with shocks. And here's an example. They almost all look like this. You have strong sulfur 2 and H alpha. Remember I said sulfur 2 is produced in an extended partially ionized zone when you've got the hard radiation field from shocks. So you've got sulfur 2 produced very strongly in the outer regions here, and same with the oxygen 1. And so this is a smoking gun for shocks, but we can do better than this. Because of our high spectral resolution, this is nitrogen 2, H alpha and nitrogen 2, you can actually separate your shocks into multiple components. So we have a narrow component and a broad component. And if you look at the velocity dispersion of those components, so the width, you can see that they all divide into a narrow component or a broad component. So each one of these little points here is a spaxel on the galaxy. So this is, for all spaxels in the galaxy, you have narrow components and broad components. And you can have a look at how the velocity dispersion correlates with the line ratios. So remember, shocks, particularly strong in sulfur 2H alpha or 1H alpha, the velocity dispersion correlates with the line ratio. You can't get this from things like post-AGB stars, but shocks produce this correlation. And for example, these type of velocities are typical of slow shocks, 100 to 200 kilometers per second. These type of velocities, 40 kilometers per second, are typical of H2 regions. It's just regular turbulence. And so we can do things with the IFU data, like, for example, we can color code our broad component and our narrow component, shock component, H2 component. We can put it on their diagnostic diagrams, and these allow us to separate power sources, these diagrams. So typically star-forming regions lie here, AGN lies here, shocks typically go out here. And so you can see that our narrow component is in a different region to our broad component. The broad component comes out in this direction, and same for this galaxy. These are two different metallicities. This is a lower metallicity galaxy to this one, so they're in slightly different positions. But we have the broad component that is consistently further out than the H2 component. So this indicates a different power source. And we can create shock models. Now these shock models we made these before we got the observations. And we found it remarkable that the shock models actually lie where the galaxies, spaxels are. And this is the low metallicity galaxy, and each of the colors corresponds to mixing lines between the star-forming regions. Pure star-forming regions are in blue, pure shocks are in red. And so we've got mixing in every spaxel between star formation and shocks, and same for this galaxy here. What this means is you can calculate the fraction of shocks based on these models and these diagrams to every emission line, to every spaxel across the galaxy. So this is really powerful, because then you can calculate the fraction of shock contribution to your individual galaxy, but then into your whole sample for every emission line you want to look at, as long as you've resolved your separate components with the high spectral resolution. And so we did that, and here's an example of the sort of thing you can do. This is your fraction of total H alpha versus merger stage, and how much do shocks contribute as a function of merger stage. So shocks and don't contribute much to isolated galaxies or wide pairs. Close pairs, they contribute up to about 30%, and then at the late merger stage you're dominated by shocks, even in H alpha. And the star formation dies down towards late merger stage, and you're almost all dominated in H alpha actually by shocks. These shocks are from star formation driven outflows. We've removed all the AGN from our sample, and that's optical, infrared and X-ray AGN. And so these are either outflow, starburst driven outflow shocks, or they can also be shocks driven by gas collisions from the merger process itself. And when we looked at very high resolution with in the near infrared with adaptive optics, what we find is there's both. So you can see where there's a bridge between the two nuclei, there's shocks along the bridge, which indicates collision shocks, and you also have wider, larger scale shocks, which would be presumably from starburst driven outflows. Okay, so at these late merger stages, I said I removed the AGN, and that's because we couldn't separate star formation from shocks and from the AGN, but we're still trying to do this, and I'm going to show you very exciting results of how we can do this. So first I'm going to show you how we separate star formation from AGN. Okay, so these are individual spaxels within the same galaxy. This is the line diagnostic diagrams where we traditionally use to separate star forming from AGN. So the AGN have a harder radiation field, so they're up. The AGN dominated spaxels are up here. Okay, what is in here? What's in the middle? These are traditionally called composite regions, or composite, or if a galaxy overall lies there, it's called composite galaxy. But what does that mean? Well, we can take those spaxels and then color code them on the image of the galaxy, because it's IFU data, and we get a ring. This is the narrow line region radius in this galaxy, this ring. So there's a very easy way of measuring the narrow line region radius. Within this ring, you're dominated by star formation. Within this ring, you're dominated by AGN. Outside this ring, you're dominated by star formation. If I get my words wrong, it's because it's now it's like a 12-hour or 8-hour time difference to Australia, and it is certainly in the middle of the night for me. Now we can do even better than that, calculating one ring. We can color code up the sequence, and you get more rings. So what this means is within this region here, you're dominated 80% by AGN, 80 to 100%, and then this is now 80 to 60%, and then you've got 60 to 40% AGN, and then 40 to 0% AGN in the outer regions. So you can see that if we then use models to calculate the fraction up here, or we can do it empirically, you can do it either way, we've done it both. You can then calculate your star formation to Aegean fractions in galaxies. And how well does that work? How well does it work when we calculate the star formation Aegean fraction? So we can do that, and then we can subtract the AGN and measure star formation properties, or we can subtract the star formation and measure the AGN properties. And they are both contributing before, because these are kiloparsec scale spaxels. So here's an example. So in this galaxy here, we've got HST data, and we measured the H alpha. If we subtract the AGN, we'd measure an H alpha star formation rate of 1.3 solar masses per year. And this is similar to the 8 micron star formation rate of 1.48 solar masses per year. If we didn't subtract the AGN, we would have derived a H alpha star formation rate of 2 solar masses per year, so significantly larger. So this indicates that the technique actually is working, and it will enable us to measure the star formation rate in galaxies containing an AGN, even in the pixels where you've got both happening. It's really exciting. And you can also subtract the star formation from the AGN. So for example, the oxygen 3 line, and measure AGN properties. So we can do that. Here, the AGN bolometric luminosity derived from O3 is 5.9 times the 43 ergs per second, and it compares really well to the X-ray bolometric luminosity here, and it's actually the same within the errors. If we didn't subtract the star formation, we would have a significantly larger bolometric luminosity from the AGN. So it's important to do this, and now we finally can. We've been trying to do this for decades, and we really needed a high spectral resolution integral field data. Okay, so the other interesting thing you can do with AGN, they don't all show rings, but you can actually you can see the ionization cone in these galaxies. So here's the 2 very beautiful ionization cones. You can actually measure the AGN contribution across the ionization cone. And in other galaxies, you've got a very large Aegean narrowline region, and then outside that, within the spiral arms, you can see the star formation regions. And then up these sequences is how we separate the star formation from the Aegean. Okay, so here's some results. This is some science that we can do now. So this is galaxies from Sloan, so not integral field data anymore. But we can use the theoretical models that we derived, which are constrained by our integral field data, and now we can derive starburst Aegean fractions up this mixing sequence. And so these ones, we're taking our starburst models and our Aegean models, so these are photoionization models, and using a Bayesian technique, just putting the spectra in there with no assumptions about what fraction of starburst to Aegean there is in the galaxy, and then the Bayesian fitting decides what fraction of star formation to Aegean you have. The models have been constrained by our observation. So for example, we're constraining the electron density, the ionization parameter range, things like that. And this produces a mixing sequence. So our resulting starburst Aegean fractions, which come out of the fits, produce a mixing sequence which we can color code like before with the integral field data, but this is now not integral field data. We're measuring starburst Aegean fractions in global spectra. And so what this is showing you is that most galaxies up this sequence are actually still dominated by their star formation until the ones right at the top, which are dominated by the Aegean. So that's a result for Sloan. We can also now derive metallicity in Aegean for the first time, and this is really recent work. Adam actually he's actually just submitted that paper just a couple of days ago, and this map shows metallicities across the starburst sequence down here, so low metallicity, high metallicity, but now we can do metallicity for the Aegean, and you can see there's actually they're mostly they're metal-rich galaxies, and that's what we'd expect because Aegean typically reside in high-mass galaxies, and there's a mass-metallicity relation, so high-mass galaxies have higher metallicities. But there's also a little gradient across here you might not be able to see at the back. It goes from red to yellow, and so that means there's a little bit of a gradient in metallicity across here, which is what we expect from theoretical models because the N2H alpha line is sensitive to metallicity even in Aegean. We can also now measure a mass-metallicity relation for Aegean and compare that with the mass-metallicity relation for star formation. So there's a well-known mass-metallicity relation for star-forming galaxies, which is shown here in blue, and there's a good correlation, and then it turns over, and now we have Aegean on here as well, shown in dark red, and the Aegean lie in a very similar place to the star formation mass-metallicity relation, except that they're a little bit offset low, and at the moment we don't know why there's an offset slightly low. This could be a real effect. It might be that the N/O ratio we're using in our Aegean is not the N/O ratio you see in Aegean. Maybe they're more enriched, but also it could just be a systematic from the fact that we're applying theoretical models both for the star forming regions and for the Aegean, and if there is a parameter in there that's not the same as is in reality on average, you can get offsets. And it must be a parameter that is differently constrained for the Aegean than for star formation to get this difference. Okay, so now we can separate star formation from Aegean. I showed you how we can derive metallicity now and mass-metallicity relations for galaxies with Aegean, and these were Sloan galaxies, so this is good new stuff. But what we have at the late stage mergers is not just star formation Aegean, we've got shocks as well, and shocks are pretty much everywhere in those galaxies. So we've been working for a long time on trying to separate shocks from these galaxies, and we think we finally have the answer. And my student Josh was determined to do it. He said, I'm going to do it, it's driving me nuts, the shocks are driving me nuts. And so I said, well, try velocity dispersion. And so here he's got a plot of radius versus velocity dispersion and a line ratio. This is O3 H beta. And what's happening in this plot is because we've got velocity dispersion and radius, it actually allows you to separate shocks from AGN because they tend to mimic each other on the 2D diagrams. And they're being separated. So this one, it's a little bit hard to see, but the star-forming regions are across here. So in the zero velocity, or about 40 kilometers per second. So here, that's just star formation. And then the AGN have very strong O3H beta, so they're coming up here. AGN comes up there. And the ones that come right out, these are shocks, like that. And so here's another example. This is a different galaxy. We're doing it with different resolutions just as a check. This galaxy is a spiral galaxy, grand design spiral. It's got a little AGN in the center. And so this is the star forming sequence here. It's fairly flat on the plane. And then on this side, we're color coding according to AGN, maximum AGN. So here's your AGN sequence, star formation to AGN. All this is shocks. Here is color coded according to the fraction of shocks. And so there's some shocks coming off in this region. So a typical galaxy will look like a fork on this diagram, a bit like this, where you've got an AGN sequence and a shock sequence. We're now fitting this to derive shock fraction, AGN fraction, and star formation fraction for the same galaxies. And that's work that's in progress. Now, how well can we do this with spatial resolution? Remember, we've got our typhoon galaxies, and we've got 40 parsecs resolution, so how well can this be done? I'm just going to show you this in 2D, but it's the same in 3D. It just starts looking pretty messy because there's so many spaxels here. But here's our star forming sequence. This is the sequence up to the AGN. And now we're going to step down in resolution. So here now we're going down to 330 parsec resolution. So that was our original. Oh, that's degraded more. So I'll start again so you don't get confused. Okay, native resolution. Step down, step down, step down. Now we've got kiloparsec resolution. That's what we get with SAMI and MANGA, and at high redshift. You can still see a mixing sequence, and within the coarser resolution, you'd still be able to get your starburst AGN fraction. So this is good news for being able to separate starburst from AGN. We're now checking out how well we can do this with the shocks. What is also interesting is that as you degrade in resolution, you're actually picking up low surface brightness emission that you didn't find at the finer resolution, because you're spreading your light out over more spaxels, and so you don't pick up the low surface brightness emission from the AGN. And so it's actually they're complementary to each other. Okay, so I'm going to just give some conclusions and then a quick look into the future. I think we're in the beginning of a new field. We're able to now separate out these power sources, which means we can actually measure the fundamental properties of galaxies for the first time. And I think I just showed you a few of the science results that we've just got out, but we're really just scratching at the surface. There's a huge amount more to be done with all these galaxies, especially now that we have 3,000 galaxies in the SAMI sample. We want to measure these things as a function of environment, so star formation, AGN, shocks as a function of environment, inflows, outflows. And so I'm very excited to be able to be working in this area at the moment, because there's so much happening. It's great. We have a lot of tools from integral field spectroscopy. Okay, so to conclude, I showed you that our metallicity gradients, we can see flattening in mergers, but that gradients are not great if you have coarse resolution like a kiloparsec resolution. You really don't recover gradients well because of the diffuse ionized gas. But you can measure outflows very well with integral field spectroscopy, and that's because of the velocity information as well as the line ratio information. We can measure mass metallicity relation with AGN because we can now separate star formation from AGN, and we can now separate a starburst and AGN and shocks. And so look into the very near future, we'll be doing this for many more galaxies, and then doing that as a function of, for example, merger stage, as a function of environment, and interesting results to come. Okay, so just a few future directions. So this work was one of the inspirations for a big proposal I put to the Australian Research Council. It's a $40 million centre, and we're very lucky we got it. And the science goals of this centre are to really understand galaxy formation evolution in 3D, and in particular, what are the ionising sources? We've got really excellent radio telescopes in Australia that are very sensitive, and there's not much noise because they're in the desert. And they can, over 7 years, we're hoping we'll be able to detect the epoch of reionisation. We have radio arrays which can measure H1 in galaxies, and for the same galaxies that we can have our optical data. So we can measure neutral gas, ionised gas and stars for the same galaxies in 3D, which is very exciting. And then we're combining this with gravitational lensing to build up our number of galaxies with data cubes across redshift. And so we're trying to understand, how did the ionising sources change with time? How did mass and angular momentum change across time? How are we building up galaxies? And how did the chemical elements build up in galaxies across time as well? And so there's lots of positions for postdocs. Keep an eye on the AAS job register. There's about 150 people involved in the centre, and it's an exciting time to come and visit Australia. So drop me a line if you'd like to visit, or if you want to apply for a job. Thank you.
So, many thanks, Lisa, for this exciting overview about what we have learned about galaxy evolution in the past years. And I'm sure there must be many questions. The podium is open. Who wants to start?
I'm told you have to count to 10 before people will put their hands up.
Yes, Freke.
In your plot that showed the BPT diagram with metallicities, there were also lots on the Aegean sequence that are actually low metallicity, and I don't think you mentioned those, did you?
No, I didn't. I can talk about those. Yeah.
What kind of objects those are?
Let's go back. This one?
Yeah, but there's this blue blob at the bottom instead of the green.
Oh, these ones, yeah. So these are classified as liners. So they've got low ionisation emission, and liners so they've probably got they're different to regular AGN. They've got a different, if they're AGN, they may not be, not all of them are AGN, but some of them have got a low luminosity AGN in them, and they're accreting inefficiently, and so they've actually got a different ionising radiation field. And so we haven't incorporated that yet, so they're black because I didn't...
Oh, they're black?
They're actually, you can't see it, but they're black. And the other thing is that a lot of galaxies in this region are actually shocked, and we haven't yet measured the metallicity for the shocks. That's next, but we just haven't got there yet.
Okay,
yeah.
Exciting.
So, who's next? Volker.
I was intrigued by one of the results on your mass metallicity relationship, where you showed that the AGN metallicity in this plot, right? You seemed like you didn't quite trust the result that the AGN metallicity was lower.
Yes, it could be real, but the reason I don't trust it is because if you look at the different metallicity calibrations just for pure star formation, there's actually an order of magnitude difference between them in the absolute metallicity that they predict. And it depends on the theoretical, within the different theoretical models, there's about a 0.2 Dex offset. So from here to here, between different calibrations, just based on different models. So I'm reluctant to say that that's real at the moment. It could be, but we haven't investigated at the moment yet fully whether we can reproduce this just by changing some of the model parameters.
Yeah, it's curious. We see for quenched galaxies, AGN quenched galaxies, a slightly lower metallicity at this mass range in the hydro simulations.
Okay, so I mean this could be real, but I want to check the other things first.
So let me intersect a question. I'm wondering about singly ionized carbon, the C2 line. If you had C2 data for many of these galaxies, would that be useful? The background of my question is we are putting together a fourth generation instrument proposal for SOFIA, which could probably map some or many of these galaxies.
Yes.
Would that be an interesting science?
Yes, so one thing I didn't talk about at all is that we've just got a new grid of diagnostics, which it's a 3D grid, so it's got pressure, ionization parameter, and metallicity. And I've just made diagnostics from the UV through to the far infrared. And so some of them do have the carbon-2 line. There's lots of other lines that we've got diagnostics for now. I've just submitted the pressure diagnostics paper. The ionization parameter paper is about to come. And then there's the metallicity ones are all going to be in an annual review that I'm submitting in September. Okay. But so yes, and we should talk. I mean, I can show you some diagrams offline. I don't have them easily accessible within PowerPoint, but there actually are a lot of diagnostics that you could use that are sort of hot off the press.
Okay, we do that tomorrow. Then. Further questions? Wow. Yes, Irene.
I have really lots of questions, but is there a bar event after this talk?
Oh, I hope so. I hope there's a bar event after this talk. She said a bar event.
Bar event where we can discuss things with, because I don't want to attack you with my hundreds of questions. Thank you.
I'll be happy to go to a bar and answer your questions.
So, are all questions deferred to the bar, or are we having more discussions here? So I guess it is the heat, and you explained everything so nicely. Good, I see no more hands up. Before we thank the speaker, let me announce next week's colloquium, which is also about galaxies, a specific galaxy, our own Milky Way, where we have fantastic resolution. We will have Sergio Molinari from Rome visiting us, and he talks about galactic plane surveys from the galaxy down to star-forming cores and back again, what we can learn from these type of large surveys. So, the bar event was mentioned. If you're interested in meeting with the speaker, please come down here. We will go to the Neuenheimer Marktplatz to have drinks, alcoholic or non-alcoholic. And then afterwards we will just slide into dinner. Please let me know if you want to also come for dinner or just come down to the Neuenheimer Marktplatz at around 19 hours, 7 o'clock. Good. With that, many thanks again, Lisa, for this fantastic talk.
Thank you.